And welcome to the first episode of AlgoSmash. Today we'll be tackling the very famous subarray sum problem, but before we jump right into it, let's first have a quick primer on subarrays. What exactly is a subarray? A subarray consists of contiguous blocks of indices taken from an array. If we take the very simple example of an array containing values 1, 2, 3, and 4, this array is 0 indexed, so the indices are 0, 1, 2, and 3. And someone asks us to list or print all the subarrays of this particular array. How will we get started? Well, we can get started first with element at index 0, index 0, index 1, index 0, index 1, index 2, index 0, index 1, index 2, and index 3, element index 1, index 1, index 2, 1, 2, 3, 2, 2, 3, and index 3. These are basically all the subarrays that can be found from this particular array example that we have taken. To make this more clear, if we take 0, 1 subarray, we are telling the subarray starts at index 0, ends at index 1. So this will have values 1, 2 because 1 is at index 0 and value 2 is at index 1. If we say 0, 1, 2, 3, this is basically the whole array and it will have values 1, 2, 3, 4 because this subarray starts at index 0 and ends at index 3. If we say 2, 3, what does that mean? It means that this subarray will have values starting from index 2 of the array and ending at index 3 of the array. Hence, it will have values 3, 4. Hope that is clear. Another thing you must have noted is that every subarray can be distinctly characterized by two things, the start index and the end index together. So both are included, hence the square bracket here. The single element subarrays can be taken as a special case where S equal to E. The start index is equal to the end index, hence they can be rewritten as 0, 0, 1, 1, 2, 2, and 3, 3. A good question to ask yourself at this stage is, given an array of size n, how many subarrays can be formed? A hint from my side is, if you look at the first column, you have n entries, second column n minus 1, it keeps decreasing by 1, and at the last column you have 1 entry. If this reminds you of something, great. Otherwise, you should remember that this is nothing but the sum of natural numbers starting at 1 and ending at n. So this is nothing but 1 plus 2 plus 3 up to n. This is n into n plus 1 by 2. Given an array of size n, we will have n into n plus 1 by 2 subarrays exactly. That is why for this particular example where we have n is equal to 4, we have 10 subarrays because 10 is equal to 4 into 5 by 2, which is n into n plus 1 by 2. Hope all this is clear, and we can go to the next main meaty part here, which is finding out the maximum sum subarray or printing out the maximum sum subarray. So let's have a look at this stage. Maximum sum. So for this problem, it should be noted that the array can contain positive as well as negative elements. Why is this explicitly mentioned? This is because if you have a simple array containing values 1, 2, 5 and all positive values, you know that the maximum sum subarray, if you have to print the maximum sum, this is basically the whole array itself. There's nothing to think here because if all the array is positive, if you keep adding positive values to the array, the sum will keep growing, and the maximum sum you can obtain is the sum of all elements present in the whole array. So this is not something we will solve. This is a trivial case. So we are more concerned is with the part where positive and negative elements are there. For example, we take this array containing values minus 2, 2, minus 1 and 6. Let's take this example here. If we have to find out the maximum sum that can be obtained from any subarray given here, what will it be? Think for a bit. Or if you are not able to visualize, this is a 3-element subarray, indices are 0, 1, 2. Like I did before, just list out all the subarrays here, 0, 0, 1, 0, 1, 2. Then you have 1, 1, 2. Then you have 2. So these are all the subarrays here. 0 means only element 2, 0, 1 means element 2, element minus 1, 0, 1, 2 means 2, minus 1, 6, 1 means minus 1, minus 1, 2 means minus 1, 6, 2 means 6. Now what is the maximum sum here? This is just 2, this is 2 minus 1 which is 1, this is 7, because 8 minus 1 is 7. This is also 7. This is 6. This is minus 1. So the maximum sum that can be obtained from any subarray from this particular example case that we have taken is 7. So our program should output 7. Let us first take a brute force approach and see how the code looks for this brute force approach, because it will give us a feel of the optimized algorithm and point us in the right direction. It's always a good approach to just try the brute force first before going on. So in the brute force approach, we have two for loops. The first for loop will go from 0 till n minus 1, and you will have a variable sum subarray that is set to 0 here. Then you will have j starting from I, and it will go till n minus 1 likewise. And here you will do sum of subarray plus equal to ARR of j. And you will check here if sum of subarray greater than the max value defined outside this for loop, max equal to sum of subarray, and you will close these two loops. How does this particular program work? So value of I is first 0. For this value of I is 0, j runs for 0, 1, 2. For example, if we have an array containing only 3 elements, we know indices are from 0 to 2, 0 to n minus 1. Now when I is 1, j runs for 1 and 2. When I is 2, j will run only once till 2. So if we take a look at this in terms of the subarray we just discussed, I is 0, we are looking at 0. So this is basically I loop contains a start indices, and j loop is continually updating the end indices. First we are looking at 0, 0. Then we are looking at 0, 1. Have a think of this way. Then we are looking at 0, 1, 2. Because we are adding the sum sub ARR of j, we are adding to sum sub at each iteration. If you are still confused by this, let me again try to explain it. In this first iteration, I is equal to 0. Then j will be 0 first. Sum subarray will have ARR of 0. That will be added to sum sub, which was 0 initially. Hence it has ARR 0 here. Sum sub has ARR of 0. This max will be updated here. Then you go back to the j loop. J will be 1. Sum sub already has ARR of 0. So ARR of 1 will be added to this sum sub. Now sum sub has ARR 0 plus ARR of 1. We are checking if sum sub greater than max, and this will be updated. Then what will happen? J will be 2 here. Sum sub had ARR 0 plus ARR of 1. Now you are adding ARR of 2 there. So it will become ARR of 0 plus ARR of 1 plus ARR of 2. Again you are checking if it's greater than max and updating. Then the inner j loop ends, you go to the outer I loop. I becomes 1. Then you come down. J becomes 1, and sum sub was initialized to 0 here, you see. So now sum sub will have ARR of 1. You again check if it's greater than max and you update it. Then you go back to the j loop. Now j is 2. Now what did sum sub have? ARR of 1. Now it has ARR of 1 plus ARR of 2, and so on and so forth. This is O of n square. As we already know, the number of subarrays are n into n plus 1 by 2, and we are looping through this loop, 2 loops here, and it's O of n square. Now why is this an issue? Well, if n is 1000 or n is 100 or n is 10, 5, or these small values, it isn't really an issue, because this loop will get executed pretty fast. Because even if n is 10 to the power of 3, 2 loops, so we're doing approximately 10 to the power of 6 operations. The problem arises when the value of n is so large, like n is say 10 to the power of 5, then these 2 loops are going to take forever to run, and it's not optimal or efficient. So to combat this, we're going to have a look at Cadence algorithm, which is to solve the subarray maximum sum problem in O of 1. This is a TP based approach, but don't get scared. We'll just have a look at it. Now, if we are going to enumerate all the subarrays ending at index 0, what will these be? These are basically keeping track of ending at index 0. So only the subarray ending at index 0 is 0. If you want all the subarrays ending at index 1, what will it be? We will have 0, 1, and you'll have 1 alone. If you want to enumerate all the subarrays ending at index 2, you'll have 0, 1, 2, you'll have 1, 2, or you'll have the element index 2 alone. If you want to enumerate all the subarrays ending at index 3, what will these be? 0, 1, 2, 3, 1, 2, 3, 2, 3, or element index 3 alone. Do you see a pattern here? If you don't, look at the subarrays ending at index I enumerated here with respect to subarrays ending at index I minus 1. For example, here, if you look at the subarrays with respect to here, from the previous subarray, we are adding index 1 here so that it ends at index 1, and we have separately index 1 here. If you look at the subarrays ending at index 2, we look at all the subarrays ending at index 1, and we are basically adding this element at index 2 to those, and we have a separate element here, that is index 2, element at index 2. Now if we look at the subarrays ending at index 3 with respect to the subarrays ending at index 2, basically take all the subarrays ending at index 2, add the index 3 here so that they end at index 3, and we have index 3 separately. This is a very important thing to understand in order to get the intuition or feel of solving using Cadence algorithm. And if you don't get this, I suggest you take an example of different arrays and just walk through these subarrays. List down all the subarrays and write down subarrays ending at index 1, 2, 3 till n minus 1 and so on. Now, the main thing or main takeaway that we got here is subarrays ending at index I is all the subarrays ending at I minus 1, you add ARR of I, the ith element there, or you have that index alone. For example, all the subarrays ending at index 3 will be found out if you take all the subarrays ending at index 2, you add the ith index there so that all of them end at index 3, or you have the element at index 3 alone. So to drive this home, just remember that suppose we want all the subarrays ending at index 4 and you already have all the subarrays ending at index 3. What will you do? You will take all the subarrays ending at index 3, you will add the element at index 4 at the end, and you will also take the case where you are looking at only element at index 4 because that also ends at index 4, right? So this is the main thing here. Now if we want to see the code for this particular approach or Cadence DP approach to solving this problem, we have a DP array. What does this DP array track? It tells us the maximum sum that can be obtained if we look at all the subarrays ending at index I. DP of I tells that. DP of 0 is ARR of 0, because if you look at all the subarrays ending at index 0, it is basically only that one element, and you cannot do better than one element because the only subarray ending at index 0 is that particular element. Okay, now for all the other things we run a loop from 1 to n, and what we do, we tell dp of I is the max of dp of I minus 1 plus ARR of I or ARR of I alone. So let's take a moment to understand this. dp of I stores the maximum sum that can be obtained by a subarray ending at index I. As we saw before, dp of I stores the maximum sum out of all the subarrays ending at index I. So for this, we look at all the previous subarrays ending at I minus 1 and we add ARR of I to it. Basically, again, I'm repeating this because this is important. dp of I stores the maximum subarray sum of the subarray ending at index I. So to find dp of I, we look at the maximum subarray sum obtained at the subarray ending at index I minus 1, and we add ARR of I to it. Or if we are going to form a new subarray looking at only this particular element at index I, we take ARR of I alone. So this is important. dp of I is max dp of I minus 1 plus ARR of I, which signifies dp of I minus 1 is the maximum sum obtained by a subarray ending at index I minus 1, and you add ARR of I to it, or you start a new subarray from this index, so it's ARR of I. Now question to you is, will this work after running these two this loop? If we just return dp of n minus 1, will it work? Will it work? So the answer is no, this will not work, because dp of I stores the maximum sum obtained from a subarray ending at index I. You have to loop through the dp array after it's computed and return max of the dp array. Return max of the dp array. So suppose you have a dp array that's populated for an array of size 5. So you'll have dp of 0, dp of 1, dp of 2, dp of 3, and dp of 4, with dp of 0 representing the maximum sum that can be obtained with a subarray ending at index 0, dp of 1 maximum sum obtained at a subarray ending at index 1, dp of 2 means maximum sum that can be obtained by a subarray ending at index 2, and so on, and you find the maximum of all these subarrays. So that was Cadence algorithm. Hope you understood something new, and this is my first video, so give me some suggestions in the comment box, and I'll see you in the next video. So see ya, tata, bye bye.